One final example we're going to look at is related to a different data set, so no more pop bottles on the machines. This time we're looking at SAT scores. Okay. In 2006, the mean and standard deviation for the math portion of the SAT were 518 and 115 respectively. If Quinn scored a 697 on the math, what percentile is he in? Keep in mind, SAT scores are normally distributed. So that means if they're normally distributed, you see that normal curve below again. Now, as we saw with machine 1 and machine 2, there were some things that stayed the same. Namely, these percentages did not change. If it's normally distributed data, these percentages are what they are. But what was different each time? Well, what changed was the x-axis, because we had to label that specifically for the data set we were working with. So in this case now, the mean is no longer 12, it is 518. We're going to go ahead and label the x-axis the same way we did before by adding on the standard deviation and subtracting it appropriately. So to get this point, we'll go ahead and add on the standard deviation of 115 once, we'll add it on twice, and we will add it on a third time. To get the points to the left of the mean, we subtract the standard deviation once, twice, 3 times. Now, the question is that if Quinn got a 697. Okay, this is a little different than the problems we had before, because with machine 1, we were talking about a data value of 10.59, and it turned out to be one of our labels on the x-axis. When we were talking about machine 2, it was a data value of 12.28, and that also happened to be a label on the x-axis. But notice now, in Quinn's case, we're looking at a score of 697. And as I look along the x-axis, I do not see 697 anywhere. But it is actually there. Okay? It would live between 633 and 748. That's where 697 falls. What you have to keep in mind is it is absolutely impossible to label every possible data value because our x-axis would just get too cluttered. So we choose these points, our marking off points, that we write on, and they are just serving as a frame of reference. So given the reference points, we can see that 697 would fall between 633 and 748. We could sit here and try to figure out exactly where it is. Sometimes it's obvious if it's closer to one data value or another. 697 is just about halfway between 633 and 748. Now this question is also a little different because it's asking for Quinn's percentile. So here it doesn't explicitly say that I want to be less than his data value or that I want at least, which implies being to the right of. It's talking about percentile. But remember, we already talked about percentiles. And percentiles always tell us the percent of data below. So the fact that that word percentile is in there indicates what direction we need. Percentiles always tell us the percent of data below. In other words, we need all of these percentages. All right, well, we're going to combine all those. I think it's fair to say that Quinn did better than all that 2.35% and this 13.5%, as well as this 34 and this 34. The issue we run into now is with this piece right here. You might be thinking that, well, since 697 is halfway between here and here, then I should just take half of 13.5, which would be 6.75, and that's what I should add on. But be careful with that, because remember, these percentages are based on area and size of the pieces. Look at the size of this that I've shaded versus the size of this to the right. They're not the same. So they don't get equally, they don't share equally in that 13.5%. Taking half, that 6.75, is a great place to start. But this piece right here is bigger. So we have to give it more. We've got to go up. How much more? Well, your guess is as good as mine. It's an approximation, to be quite honest. To call it 6.75 would be wrong, and to call it less than 6.75 would be wrong. But if you wanted to call it 7, and your classmate wanted to call it 8, and somebody else wanted to call it 9, None of you would be wrong because it's just an approximation. So I'm going to go ahead and add on 10 just because 10 is a nice easy number to add on. All right, so the question was, what percentile is Quinn in? If I add up all the percentages that fell below Quinn's data value, I get 93.85%. So that puts him in approximately the 94th percentile. So he did better than about 94% of the people who took the exam at the same time as him. Now the problem is that this was an estimate. Okay, so in class we're going to talk about how to avoid that. Furthermore, I don't know how many of you were getting sick of drawing, well, you didn't have to draw the normal curves, but you had to relabel the x-axis every single time, even though these percentages stayed the same. In the following videos, you're going to see a shortcut to all of this. Okay, so in the videos, you're going to see a shortcut where we don't have to work on a separate or unique normal curve for each data set. In class, we're going to talk about how to avoid doing these estimates. Because while an estimate is okay, sometimes we need accuracy. Think about it. If somebody else called this 7 instead of 10, that would have put Quinn at the 91st percentile. That really could make or break his entrance into a college. Being in the 91st versus the 94th could make a difference. So while approximations or estimates are okay, there is often a need to be more accurate. So in the next videos, we'll talk about a shortcut to this whole process, and in class, we'll talk about how to avoid estimates.